Alright guys, Mr. B here again. This video is going to be going over the chapter 26.2 notes and the practice questions, so if you are confused on any of the questions there, hopefully this video will help you. Alright, taking a look at number 1. Circle the letter of each sentence that is true about a light year. It is a typical unit of measure for distances on Earth. Definitely not. A light year measures a very large amount of distance. Earth is very small, so we do not use it to measure distances on Earth. B is at a distance of about 9.5 trillion kilometers. That is true. So it's a very long distance. It is a distance that light travels in a vacuum in a year. That is also true. That's why we call it a light year. So it is the distance that light travels in 1 year in space. And letter D, it is a unit of time. That is false. It is not a unit of time. Even though it has year in it, and years are usually measures of time, a light year is a measure of distance. So don't get that confused. Number 2, true or false, parallax is the apparent change in position of an object with respect to a distant background. That is true. So parallax is where it looks like something is moving, like its position has changed with respect to things behind it, but in reality, it hasn't moved at all. It's the observer that has moved, or the viewpoint that you're viewing it from that has moved. So, number 3, astronomers measure the parallax of a nearby star to determine its distance from Earth. Okay, so we use parallax to determine the distances of stars from Earth, typically ones that are relatively close. Parallax doesn't work for things that are really far away. It only works for things that are somewhat close to us. So we have other methods for finding distances to further away stars, but still a good method to use. Number 4, circle the letter of each property that astronomers use to classify stars. So we classify stars by brightness, so that's 1. We classify them by color, that is 2, and we classify them by size, that is 3. We do not use distance to classify stars because stars can be close, far away, that doesn't matter. We only classify them based on how they look, how big they are, their color, how bright they are, stuff like that. So, number 5, true or false, the brightness of a star as it appears from Earth is called its absolute brightness. That is false. The brightness of a star as it appears from Earth is called its apparent brightness. So that's how bright it looks like it is from Earth. Its absolute brightness is its true brightness. So, yeah, that's false. Number 6, a star's blank can be used to identify different elements in the star. This is a star's spectra, or spectrum. Either one is fine. But a star's spectra can be used to identify different elements. That's where you have a big, basically a bar of like colors, like the rainbow, and then there's black lines that are in there, and that tells you what elements are in there. It's called a star spectra. Number 7, describe the chemical makeup of most stars. So most stars are made of primarily hydrogen and helium. Okay, there are other elements found in stars like oxygen and carbon and stuff like that, but primarily they're hydrogen and helium. Older stars that are close to dying will have heavier elements like iron and stuff like that, but the biggest percentage of stars is hydrogen and helium. So, because that's how nuclear fusion works, it fuses hydrogen to make helium. All right, number 8, circle the letter of each way that HR diagrams might be used. It was a good question. So, HR diagrams can be used to study sizes of stars. Yep, that is true. They can be used to study distant planets. Nope, HR diagrams aren't used at all for planets. They only are looking at stars. So planets aren't on HR diagrams, so that would not be a good answer. They can be used to determine a star's absolute brightness. That is also true. On HR diagrams, we are looking at absolute brightness on the y-axis and temperature on the x-axis. So, and then letter B, to determine a star's surface temperature or color. That is also a good way that we can use HR diagrams. Because again, on the x-axis of an HR diagram is surface temperature and also color. So those would be the 3 good answers. So, all right, number 9, circle the letter of each sentence that is true about supergiants. They are found at the upper right of the HR diagram. That is false. They are on the upper left. The upper right are the giants, so that's not true. Letter B, they're much brighter than main sequence stars of the same temperature. That is true. There can be a main sequence star that is the same temperature, but supergiants are way brighter, primarily because they're bigger, so they have more surface area for more light to come out. The best way to think of it is like a supergiant is like a super big floodlight, right? That has like lots of light that comes out. And a main sequence star is just like a little flashlight bulb in your flashlight. Not nearly as bright because it's not as big. Okay. Letter C, they are 100 to 1,000 times the diameter of the sun. That is true. They are way bigger than the sun, hundreds of thousands of times bigger. So yeah, that's why they're called supergiants. And then lastly, letter D, they are smaller and fainter than giants. No, that is false, right? They are supergiants, so they're clearly bigger and a lot brighter than regular giants are. All right, last question here. Number 10, how does the brightness of white dwarfs compare to the brightness of main sequence stars? White dwarfs are way smaller than main sequence stars, so the amount of light they give off is way less. Again, if you want to think of the flashlight analogy, right? You know, a main sequence star might be a flashlight that you hold like in your hand, like a regular one, and a white dwarf would be like one of those tiny little miniature flashlights that you get from like the gas station. You push the little button, it has like that little LED on it. They're not usually that bright. So we can say the brightness of a white dwarf is much less than the brightness of a main sequence star because it is much smaller and has much less surface area. Something along those lines, right? But they're much less bright. So, all right, that is all that we have for this section of notes. So hopefully that helps you. And as always, if you have any more questions, you can always let me know. And I will see you in the next video, guys.